Hello everyone, welcome to the another lecture of chemical bonding class 11. Myself Suman Singh. So in the last class we have discussed about the molecular orbital theory and how to draw the molecular orbital theory. So now in today's class we will learn about the resonance and hydrogen bonding. Okay. So what is resonance? We know that covalent molecules are normally expressed in Lewis structure, but in some cases single Lewis structures fail to explain all the characteristics of the molecule. For example, you can take the example of this ozone. As you can see, you can take the example of this ozone. Okay, so the a single Lewis structure fails to explain all the characteristics of this molecule, right? Here, if you will see closely that the two bond in the molecule are expected to have a different values, right? Two bond in the molecules are expected to have a different values. But the experimental studies shows that both the bonds have a same length, which is 128 pm. Okay, and moreover the bond length is intermediate between the single and a double bond, as you can see here, right? The bond length is intermediate between the single and the double bond. Now the problem can be solved if we consider that the ocean is capable of existing in two forms in which the position of the double bond and the single bond are interchangeable, right? How we can solve this problem? So to solve this problem we can consider, or if we consider the ocean is capable of existing in two forms in which the position of the double bond and the single bond is interchangeable, right? As you can see in case of this, like this, means what? Sometime double bond, sometime triple bond is changing like this, right? Is like this, right? So if it is interchangeable, if we consider, right? Now such structures for the molecule is known as what? Resonating structure or contributing structure, separated by a this sign. Okay, separated by this sign, right? As you can see, this is structure. These two are what? These two are resonating structure of each other, right? So what we have seen that the problem of this, when sometimes it is single bond, sometimes it is double bond. So if we are considering the ozone is capable of existing in two forms in which the position of the double bond and the single bond are interchangeable, then such structure for the molecules is known as what? Resonating structure. Okay, and it is separated by this sign, as you can see here. Okay, now about the resonance, this we will talk in detail about this in organic, some basic concept of organic chemistry, right? But now for just for a brief idea we will talk, I will try to give you a brief idea on this now. But when you will see, none of this structure can independently explain all the properties of the ozone. Okay, but when you will see the structure, none of this structure can explain the uh, independent explain and none of this structure can independently explain all the properties of this ozone, right? So it is believed that the actual structure is between these two contributing structure, which is known as resonance hybrid, or which is known as resonance hybrid, as you can see here. This is called a what? This is known as resonance hybrid. Okay, so what it is believed that the actual structure, which is this one and this one, the actual structure which is this and this, between these two, between these two contributing structure, one structure is there which is known as resonance hybrid. Okay, this one. So I hope you have understood this. So what we can say, the oxygen to oxygen bond in the molecule is the same for both the bonds, which is the oxygen and oxygen bond with this and this, with this and with this, right? So it will be the oxygen and oxygen to oxygen bond length in the molecule is the same for both the bond, which is 128 pm, right? 128 pm. So what we can say, how we can define now the resonance. So resonance may be defined, or we can say that it is a phenomenon as a result of which molecules can be expressed in different form. Okay, this is the phenomena as a result of which molecules can be expressed in different forms, none of which can explain all the properties of the molecule. Okay, now the actual structure of the molecule is called what? Resonance hybrid. So I think the definition is also given here, as you can see, right? The definition is also given here. This is called resonance. So I hope you have understood this, right? You have got some idea about the resonance. So what is the primary conditions for the resonance? I will try to give you a brief idea on this. So what is the primary conditions of the resonance? So first primary condition is if there is double bond, okay, single bond and double bond. For a resonance to occur, there should be double, single, double. This, if it is following double, single, double, charge, single, charge, like this. If it is following charge, single, charge, double, single, double, then only resonance is possible. Otherwise, resonance is not possible, right? So as you can see, double, single, double, right? One more example. Let me give you one more example. Charge, single, charge, right? This is also another example, right? So how there will be a movement of electron. So when we will talk about the movement of electron, always remember that the movement of electron will be from double to single. Okay, the movement of electron will be from double to single, like this, double to single, right? Again, one more example. If you are taking double bond here, single bond here, and here it is triple bond. So how the charge will move? The charge will move from double to single, and double, triple to double, and then double to fifth, and double to single, right? Like this it will move, right? Or it can move from like this, double to single, then charge, double, single, and then charge. It will move like this. Okay, or it can move like this. Suppose this is a charge here, this is a single bond here, and this is a double bond here, so it may move from here to single, charge to single. Okay, or if it is minus charge is there, and suppose here is single and here is double bond, so it can move here. So these are some of the primary condition, or we can say that the movement of electrons. So movement of electron will be always will be main. Movement of electron is main, means what? Movement towards more electronegative. Okay, movement towards more electronegative. Okay, so as you can see, one more example. Suppose this is a plus, this is a single bond here, and this is a charge here. So how will be the movement of electron? The movement of electron will be from here to here. Okay, movement of electron will be from here to here. One more example. Suppose there is a free radical here, and there is number single bond here, it is charge, minus charge, so their movement will be like this. Okay, so I hope you have understood what is the what is the primary condition for resonance. Okay, now one more example, one more thing. What is the conditions, or we can say that what is the favorable condition for writing a resonating structure? Always remember that this resonating structure is only an hypothetical structure, in the sense that none of them can be prepared in the laboratory. Okay, the molecule actually exists as an hybrid, but the resonating structure is only an hypothetical concept, or we can say that it is an hypothetical structure, in the sense that none of them can be prepared in the laboratory. Okay, so what is the favorable condition? So favorable condition is first favorable condition we can tell like this, that some same relative position of constituent orbit. First one, sorry, for atom, same relative position of constituent atom. After that, nearly same energy. Okay, after that, some same number of unpaired and primary unpaired electron, same number of paired and unpaired electron. Only electronic displacement differ, and what we can say, molecules must be planar, which is sp2. Or more, what, how we can define this? What is the condition? First condition we can say like this: the different contributing structure must have a same position of the atom. Okay, The different contributing structure must have a same position of the atoms. Now number 2, the contributing structure must have a same number of paired and unpaired electron. They differ only in their position. Next, what we can say, the contributing structure for molecules may have a nearly the same energy, or we can say at last, in all the contributing structure the like charges should not be placed on adjacent atom, right? So some of the resulting structure is given here. As you can see, the resulting structure of CO2 minus, CO3 2 minus. So like this, like this, and like this. This is the resonating structure of CO2 minus. After that, carbon and oxygen, it is like this. Benzene is like this. Benzene we are writing right like this, where we used to write benzene like this, you write. Sometimes we write benzene like this also, right? So as you can see, this is the resonating structure of benzene. After that, vinyl chloride. There are so many examples, as you can see. So many examples are there, right? Now, next is resonance energy. So what is resonance energy? So resonance energy is the difference in energy between the resonance energy is what? It is a difference in energy between the actual observed energy of the resonance hybrid and the most stable of the contributing structure is called what? Resonance hybrid, right? Means what? What we can write, resonance energy, it will be equal to energy of the hybrid minus energy of the resonating structure, right? How we can say that? It is the difference between the, and it is the difference in energy between the actual and absorbed energy, actual and absorbed energy of the resonating hybrid, and and the most stable of the contributing structure. Okay, so this is called what? Resonance energy. Okay, after that, I think resonance, about the resonance energy, it is given here also. Yes, as you can see, what is resonance energy? The difference in the energy of the colonical form or resonating form and the resonance hybrid is called what? Resonance stabilizing energy. Or we can say the resonance hybrid is more stable than any of the resonating structure. What we can say, greater the resonating structure, more will be the stability into the spaces, right? So I hope you have understood what is resonating structure. Now next is bond order in resonance hybrid. As you can see, bond order in resonance hybrid. So what is bond order in resonance hybrid? Bond order in resonance hybrid is equal to number of the bond in the resonance by number of the resonating structure. How many bonds are there in the resonance divided by number of resonating structure. So I will give you one example about the bond order, how to find out the bond order. So we can take the example of this. Suppose we are taking the example of this, right? So here you can see in CO3 2 minus bond order, what I have told you, that number of bond in resonance. Okay, so how many bonds are there in resonance? As you can see, for this we are taking 1 2 3 and 4 bond are there in the resonance, right? Let me draw it again. One, this one, this one, this one, and this one, right? This one and this one. These are the 4 bonds which are in resonance. So bond order, how we can write? Bond order is equal to number of bond in the resonance. How many bonds are there in the resonance? Which is, we have got 4, right? Divided by what? Number of resonating structures. So how many resonating structures is there? As you can see, 1 2 and 3 resonating structure, right? For this CO3 2 minus, how many resonating structure? 3 resonating structure, right? So it will be divided by 3, so we will get what it is 1.33. so the bond border of CO3 2 minus is 1.33. So I hope you have understood this, how to find out the bond order of this. Also, for example, you can take the example of this. How many bonds are there in the resonance? It's 4, right? So 4 divided by how many resonating structure? 1, 2, 2 resonating structure. It will be divided by 2. So bond order is 2, right? So in this way you can easily find out, right? Now for this also you can find out how many bonds are there in resonance? 3. So how many resonating structure? 1 only. So 3 by 1, like this you can find out, right? So I hope you have understood this. What is the bond order? Now next is rules for writing resonating structure. What are the rules for writing the resonating structure? So the first rule is the various resonating structure differ in the position of the electron and it is not in the relative position of the atom. Okay, the various resonating structure which we are getting, the various resonating structure differ in their position. There will be a difference in their position of electron and not in the relative position of atom. Okay, atom will not change, but only the electrons which is present there, it will change. Okay, now next is all the contributing structures should have the same number of unpaired electrons. Means whatever the contributing structure we will see and we will take, they also will have a same number of unpaired electron. Okay, now next is the various colonical structure show same energy. Whatever the colonical structure we will draw for any molecule, it should show a same energy. Okay, now next is resonating structure in which the resonating structure in which the negative charge residue on the electronegative atom and positive charge residue on the electropositive atom is a resonance hybrid. Okay, and when we are drawing the resonating structure, at that time we will see that the negative charge residue on the electronegative atom and positive charge residue on the electropositive atom. Okay, now last is second last is resonating resonance structure written should be written that unlike charges residue on the adjacent atom. Okay, means what, we cannot give the charge like this, one is here another one is here. We have to give the adjacent. Means if you have one you have given here, so it should be here, this will be empty, this must be empty. Okay, now next last one is resonance structure with a greater number of covalent bond contribute more towards the resonance hybrid, right? So one structure I would like to draw here for you so that you can easily understand. Suppose we have taken the example of this. Suppose there is oxygen, this is benzene ring. Okay, here one charge, double bond like this. So first of all, what will happen? Here suppose negative charge, here suppose negative charge is there, right? So first what will happen, this negative charge will come here. Okay, and this double bond which is here, this double bond will go shift here. Okay, so next structure what we can draw, the next structure will be like this. Here double bond oxygen, here this double bond here. So this, since this double bond is shifted here, so what will be here one and here one, the negative charge will come here, right? And here is oxygen. Okay, now again this negative charge will shift here. Okay, and this bond will shift here. Okay, so now next again another resonating structure will be like this. Since my handwriting means here it is very difficult to write on this, so that is why the writing is little bit dirty. So as you can see, the third resonating structure will be like this, in which here oxygen double bond is there, double bond oxygen. After that here one bond, where one bond, another one is here, and this resonating structure, sorry, this minus sign has came here. Okay, now again they will shift here, this minus sign will shift here and this will shift here. Okay, the next resonating structure will be this oxygen double bond like this, one will be double bond here. Next negative charge will be here. Now next what will happen, again it will shift here and it will shift that side, and the last resonating structure what we will get, the last resonating structure, we will get this. The same thing, from where we have started we have came to end, right? So in this way we have to draw the resonating structure. So I hope you have understood about the resonance, right? So now we will talk about the next, which is hydrogen bond. Now next we will talk about hydrogen bond. So in order to understand the concept of this hydrogen bond, let us take a molecule, say ANH, okay, in which H is likely with the strong electronegativity but a very small size, but a very small atom A, okay. So we have taken a molecule AH in which hydrogen, okay, is liked with the strong electronegative but very small atom A, okay. Here this hydrogen is liked by more electronegative, or we can say the strong electronegative and very small atom A. Atom A may be very small electronegative when we are talking, it may be fluorine or oxygen or nitrogen, okay. And they are bind together by a simple covalent bond like this. Let me see the blank pair. Blank area is here. Yes, we have taken here A and H, in which this A and H is binded with a single covalent bond. Okay, normal covalent bond. Now, when we talk about the electron pair being shared between this hydrogen and the strongly electronegative atom A will eventually lie far from hydrogen, right? Because since it is more electronegative, then it will take more electron towards itself, right? A will take more electron towards itself, right? So what we can say, there will be a partial positive and negative charge will be developed on hydrogen and A atom respectively, right? What will happen, since it is more electronegative, then there will be a partial negative, and here in place of hydrogen there will be a partial positive charge will develop, right? Now consequently what we can say, AH molecule, this AH molecule will behave as a dipole, which is represented by this, right? Which I have represented here, this. Now we know that the dipole has A as a negative end, A as a what? Negative end, and H as a positive end, right? Now, since the electronegative atom, which is A, this electronegative atom A, attract the electron pairs constituting the covalent bond between A and H almost towards itself, right? So A takes almost full possession of electron pair, that is what we can say, that A will have a lone pair of electron. Means what I means to say that, you just imagine that since A is more electronegative, so what will happen, it will pull the electron towards itself, right? And since it is pulling its electron towards itself, what will happen, they will generate a negative charge on them, right? Partial negative charge, right? But since it is attracting the electrons from this covalent bond more towards itself, though they will generate a lone pair of electron on itself, okay. And this will leave the hydrogen atom with a large partial positive charge, and AH molecule therefore will become highly polar, and hydrogen end of it will become nearly, what we can say, it will become nearly bare hydrogen nucleus or proton, which is H positive, right? H positive. So I hope you have understood this. Now next is hydrogen atom is reduced to proton, which is almost devoid of electrons, right? Now suppose if another molecules like AH same, one more molecule is there, AH same, or suppose we take BH with different, okay, with different molecules. So here if we are taking A and B are a strong electronegative atom, suppose this A, this one, if I am talking about this A and this B, if they are very strong electronegative atom which also form a dipole like A, which is also, this is if suppose this is also forming a dipole like A partial negative, A partial negative, and this hydrogen again partial positive. When we're talking about this is again B partial negative, okay, partial negative, and this hydrogen partial positive, suppose like this, okay. So if what will happen if it is represented like this is bought near AH, if this is bought if this one is brought near to this, okay, what will happen at that time? The two dipole will attract towards each other by electrostatic forces of attraction, right? This will attract this, and this will attack this, right, by a strong electrostatic force of attraction, which we can represent like this: A H plus A H, which can give A H, okay, this after that A again H, okay, and it will go on, right? So here what we are saying when we are writing here A H, and there is an attraction between again here A and H, since this bond and this bond between this and this bond is what, covalent bond, right? But this attraction which is existing between this partial negative and partial positive charge, this bond is called what, hydrogen bond, right? I hope you have understood this, right? Means suppose A is what here, partially negative, and here hydrogen is what, partial positive. Again if one more A and H we are taking, so at that time this A will attack to this positive, right? And again here H is what, partial positive, suppose. So there will exist an attraction force between these two, right? Because this is positive, this is positive, and this is negative. So there will be a attraction force between them, right? There will be attraction force between them. So since this bond is what and this bond is what, these two bond is what, covalent bond, right? And this bond, the attraction force which will exist between them, this is called what, hydrogen bond, right? I hope you have understood this. So how we can define hydrogen bond? So hydrogen bond can be defined as an attractive electrostatic force between an hydrogen atom which is already covalently attached with a strongly electronegative atom of a molecule and another electronegative atom of the same other molecules, okay, is known as what, as hydrogen bond, okay. Now under appropriate conditions, what we can say, a hydrogen atoms may be like to a two similar or different electronegative atom, and it is bounded when it is bounded to one of the two atom by a covalent bond, while to the other atom it is attached by a special type of bond which may be weaker than the covalent bond. Then it is also called what, hydrogen bond. So I hope you have understood about the hydrogen bond, right? Now next is conditions for the formation of covalent bond, hydrogen bond. What are the conditions for the formation of hydrogen bond? So the first condition is presence of highly electronegative elements, okay. The first condition is presence of highly electronegative element. So the molecule having a hydrogen atom, hydrogen bond, should have a highly electronegative atoms like oxygen, nitrogen, fluorine, okay, which is directly attached to the hydrogen atom, just like oxygen directly attached to hydrogen, or nitrogen or directly attached to hydrogen, or fluorine directly attached to hydrogen, okay. Now through a covalent bond, okay. Now next criteria is what is the conditions. Next condition will be the presence of the atom with a small size. It's the same thing what I have already told you. The highly electronegative atom should be of same size, small size, so that the so that B and H, suppose it is right, B and H, so that this B and H, where B is nitrogen, oxygen or fluorine, may be highly polar, just like this. B will be partially negative and H will be partially positive, right, partially positive, and a strong interaction between the several such dipole will occur, okay. Of oxygen and chlorine, okay. So when we will see the electronegativity of oxygen and chlorine, they are nearly same. Oxygen is supposed as 3.5 and chlorine is 3, right. But you will see that oxygen atom, due to its small size, which is about 73 7 0.37 0.73 Armstrong, and chlorine, which is 0.99 Armstrong, this oxygen will form a hydrogen bond, okay. Oxygen will form hydrogen bond, okay, with hydrogen, while chlorine, since they are having a large size, it will not form hydrogen bond, right. On the same line, what we can say, oxygen and nitrogen can form hydrogen bond, but oxygen, hydrogen and sulfur and phosphorus cannot form a hydrogen bond, right. So I hope you have understood what is the conditions for the formation of hydrogen bond. Now next we will see type of hydrogen bond, okay. Next we will see type of hydrogen bond. So when we talk about the type of hydrogen bond, there are two type, that is intramolecular or molecular or intramolecular, okay, intermolecular or intramolecular. So in intermolecular, there are homo intermolecular and hetero intermolecular. We will see one by one. So when we are talking about intermolecular hydrogen bonding, what we can say, intermolecular hydrogen bonding is that which take place between the several molecules of the same substances, or between several molecules of different substances, okay. So in this type of hydrogen bonding, two or more molecules of the same substance or different substance get uh, polymerized or associated, right. You can take the example of this. As you can see, this is the example. It is this type of bond is formed which take place between several molecules of the same substance. As you can see, several molecules of same substance. This is an H2O, this is H2O, this is H2O, right. This is NH3, NH3, NH3. There are several molecules of same substance, or the several molecule of different substance, right. As you can see in this case, HF, 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 HF and HF, right. So I hope you have understood this, right. Now next is intermolecular. Next one is next one intramolecular. So intramolecular is what? Intramolecular hydrogen bond is that which take place between the two atom present in the same molecule, okay, the two atom present in the same molecule. Now in this type of hydrogen bonding, the planar 5 member or 6 member um, ciliate ring is obtained, okay. You can take the example of this. As you can see the example of this and this. Here you can see hydrogen bond is here, hydrogen bond here, here again hydrogen bond, here again hydrogen bond is there, right. So this type of bond is called what? Intramolecular hydrogen bond, right. So I hope you have understood. Now next we can talk about the nature of hydrogen bond. So when we talk about the nature of hydrogen bond, so this it is a very weak it is a very weak electrostatic attraction between the positive pole of the hydrogen and the lone pair of the electronegative atom, which can be fluorine, oxygen, nitrogen, phone, which is called, right. But in some cases, just like in the chlorine and carbon, are also found to form hydrogen bond, okay. But this chlorine and carbon, most of the time it will not form hydrogen bond, right? Now, again, when we talk about the strength, so the strength of hydrogen bond usually very low, which is 5 to 10 kilojoule per mole. But in some cases, the value may be as high as 50 kilojoule per mole. Okay. Now, next is what we can say. The strongest hydrogen bond can be found by formed by fluorine and fluorine atom. Okay, where D is more positive than H, therefore it can also form a strong it can also form a stronger bond, right? Now next is, beside fluorine, the strength of hydrogen bond depend on the magnitude of the plus pole of hydrogen, okay, and ability of the lone pair of the atom Y, right? So now we have already discussed intermolecular, intramolecular. Intermolecular is what? Between two molecules, or we can between the molecules. And intramolecular is exists between the hydrogen and the electronegative element of the same molecule. Okay, so I hope you have understood about the hydrogen bond or type of hydrogen bond. So here some of the example is given now, right? So we have discussed this, right? Now next we will see the last topic of this chapter, which is dipole moment. Okay, the last topic of this chapter. Now next topic is dipole moment. So what is dipole moment? So we will see from here. Dipole moment is a polar covalent bond is like a dipole, right? A polar, when we see the polar covalent bond, just as in the case just now we have seen the case of fluorine and hydrogen, right? So a polar covalent molecule behave like a dipole, right? Which is also called a degree of polarity of the bond or a molecule. Okay, is expressed in dipole moment. Okay, or what we can say, the product of the magnitude of the negative or positive charge on either atom and the distance between them is called what? Dipole moment, right? What we can say, the product of magnitude of the negative or positive charge or either atom and the distance between them is called what? Dipole moment, right? Right, and which is equal to the product of the magnitude of the electric charge in ESU and the distance, which is d in Armstrong, between the positive and the negative center, that is the bond length, right? So how to represent the dipole moment? So dipole moment is represented by this, as you can see, electric charge into bond length, which is q into d, or you can see in some book you will see E into d, right? So it is represented by electric charge into bond length, which is q into d. Okay, now special unit charge of dipole moment is what? dBA. It is represented by dBA, and in which 1 dBA is equal to 1 into 10 to the power minus 8 ESU into centimeter, or you can say that 1 dBA is equal to 3.335 into 10 to the power minus 30 cubic meter. Okay, now next is what we can say, dipole moment is a vector quantity, and it is indicated by the arrow having a symbol this, as you can see, symbol this is a symbol of dipole moment pointing towards the negative end. Okay, so now we can see the example here. Between this molecule, the dipole moment will be here for this, here for this, here. So the net dipole moment is like this, right? Again, for in this case sulfur, and here more electronegative is oxygen, so this, there will be dipole moment like this. For this, there one dipole moment will be like this, so that the net dipole moment is like this, right? For here also you can see, for chlorine, for this one also, right? Now next is what we can say, greater the dipole moment, greater is the polarity of the bond. Polarity we have learned, right? Polarization and polarity we have learned in the previous chapter also. Now next is, in case of polar diatomic molecules, there is one polar bond, then so the dipole moment of the molecule will be dipole moment of the polar bond, right? When, if there is a case of a polar diatomic molecules, okay, and in there you will see that there is only one polar bond, right? So at that time dipole moment of the molecule will be equal to dipole moment of the polar bond. Okay, now next, in case of polyatomic, when there will be a polyatomic, at that time dipole moment will be resultant dipole moment of all the individual polar bonds. Okay, so some of the example is given here: dipole moment in water, dipole moment in sulfur, sorry, the dipole moment in ammonia. So as you can see, when we talk about the dipole moment of water, as you can see, since this one is more electronegative, so dipole moment will be shifted like this will be like this. Okay, the dipole moment will be the dipole moment will be like this. Okay, for this like this, so that the net dipole moment will be like this. Okay, and net dipole moment will be like this. For this also, as you can see, for this the dipole moment is for NH3, for nitrogen is more electronegative, so for this dipole moment is here. For this the electron shift is here, electron will shift right like this, right? So the net dipole moment will be, sorry, the net dipole moment will be like this, right? So as you can see, value is also given 1.49 by 1.84 by, right? Now for in case of ammonia, what is written here, you can see, in case of ammonia, in case of ammonia it is 1.49 by, right, which is equal to the resultant of the dipole moment of their nitrogen and hydrogen bond, right? Now the molecule having a zero resultant dipole moment are said to be as non-polar. Those molecule in which there will be no dipole moment, at that time that type of molecule is called what? Non-polar molecules, like CO2, BeCl2, BF2, BeF2, CS2, BF3, BCl3. These are all what? They are what? Non-polar molecules, and they do not have any dipole moment. Okay, or we can say that they have a zero dipole moment but contains polar bond. Okay, they, what we can say, they this type of molecules will have a zero dipole moment. Okay, but they are polar molecule. Let us take the example of this carbon and oxygen, CO2. This is carbon, this is oxygen. Okay, this is also another oxygen. So here it is double bond, here it is double bond, right? So when you will see the dipole moment for this, the dipole moment will be like this. Okay, let me draw it bigger. The dipole moment will be like this. Okay, for this dipole moment will be like this. But when you will see the net dipole moment, okay, the net dipole moment mu will be equal to 0, because they are cancelling, right? The dipole moment which is here and it is going there, right? So what it is happening at that time, they are cancelling each other, right? They are cancelling each other, so net dipole moment will be 0, right? So but the bond are polar. Now next, what we can say, molecular having a zero dipole moment under the following conditions. What are the conditions under which the molecules will have a zero dipole moment? So the first condition is if there is sp hybridization. Okay, the molecule will be linear geometry, right? We have learned about this. So if they are sp hybridization, they will have a linear geometry, because mu1 and mu2 will be, and mu1 mu2 will be equal, and the bond length will be 180 degrees. Just now we have seen the case of CO2, right? We have seen the case of CO2, right? That is why, because they between them they are bonded with sp2 hybridization, right? Now next, if there is sp2 hybridization, and if there is triangular planar structure geometry, as you can see in case of this triangular planar, right, and the atomic number of the central atom is less than 21, if the whatever, if there is a structure is triangular planar geometry, but if since the geometry is triangular planar geometry, right, and since it is sp2 hybridization, but you will see that the central atom is what? B is here, right? So since central atom has less than 21, atomic number is less than 21, that is why this bond will be will have a zero dipole moment. Okay. Now next is the molecule have a symmetrical tetrahedral structure. If the molecule have a symmetrical tetrahedral structure, as in the case of, you can see here, this CCl4, so that time the net dipole moment will be 0, right? Even if the case of a trans molecule, means one will be up. Trans is what, like this is trans, right? One is here, one is here, right? So this is trans. So in case of trans, you can see trans 1 2 dichlorobutene, you can see the example here. Here also the dipole moment is 0, because as you can see, this one is here, dipole moment is going out here, sorry, the dipole moment is coming out here, here also coming out here, right? So at that time the dipole moment is, net dipole moment is 0, right? No, sorry, in case of cis, as you can see, two cases are there, right? Sorry, the two cases is given here. One, this case is of cis and this case is of trans, right? But as you can see, in case of cis, the dipole moment is not 0, not equal to 0. But when in the case of trans, why it is trans, you can see one is above, one CS3 is here, another CS3 is here, one Cl is there, another Cl is here, right? So in case of trans, you can see the dipole moment is 0, but in case of cis, the dipole moment is not 0, right? Now next, if there is three different group around the double bond, then both cis and trans isomer show a dipole moment, which is, as if what it has been told, that if there are three different group around a double bond, then both cis and trans isomer show the dipole moment, which is trans and cis, right? So in case of, you can see 3,4 dichloroheptane, three different group is there. Here C2H5 is there, here CS3 there, is Cl is there, right? So at that time, suppose this is what, this is trans, right? And this one is cis, as you can see, this one is cis and this one is trans, right? So in that case, if three different groups are attached, so at that time the dipole moment will be, here cis will cis will have a greater dipole moment than trans, right? As you can see here. Now next is last one. A para isomer has no dipole moment. When there is a para isomer, at that time there will be no dipole moment. Okay, para, you know, right? If this is a benzene ring, right? So this is ortho position, this is para position, this is meta position. Okay, this is again ortho, para, meta, right? Ortho, para, meta. Okay, again ortho, para and meta. So if there is a para position, para isomer will have no dipole moment. Okay, so I hope you have understood about the dipole moment also, right? So now we will see something about the bond length and bond order, right? Now next is bond length. So what is the bond length? Bond length, I hope you have learned also in your previous class also, in previous chapters. The bond length is what is the average distance between the nucleus of the two bonded atom is known as what, bond length. In the previous chapter we have also discussed, right, in periodicity table, in periodic table. So this is the average distance between the nucleus of the bonded atom is called bond length, right? And it is, most of the time it is represented by Armstrong, as you can see here. So when you will see the bond length, carbon carbon single bond, double bond, triple bond, the bond length will follow the order this. See 1.54 Armstrong, 1.34 and 1.20 Armstrong, right? Now again, when we talk about the bond energy, what is bond energy? It is the amount of energy required to break 1 mole of bond to separate the bonded atom in a gaseous state, right? In a gaseous state, amount of energy required to break to break a bond is called what, bond energy, right? And what are the factors will affect the bond energy? Size of the atom. Okay, larger the size of the atom, larger the size of the bonded atom, larger is the bond length and lesser will be the bond energy. Okay, as you can see, bond energy is indirectly proportional to, inversely proportional to atomic size, right? Next is multiplicity of bond. If the number if for a bond between the same two atom, the the bond energy increases with the multiplication of bond, right? For example, as you can see, double bond, triple bond. So double bond, triple bond is more stronger than double bond when single bond, right? Now number of lone pair of electrons. So if greater the number of lone pair of electron present in the bonded atom, greater will be the repulsive interaction between them, and smaller will be the bond energy. Means what? If the number of lone pair is increasing, then the bond energy will decrease. As you can see, it has been clearly written here that greater the number of lone pair of electron present in the bonded atom, greater is the repulsive interaction between them, and smaller is the bond energy, right? Now next is bond polarity. When we talk about, so it will be directly proportional to polarity, right? Now again, hybridization. When we talk about the hybridization, bond energy is directly proportional to S character of the hybridization. More greater the S character, greater will be the bond energy, right? Bond angle, we all know about bond angle. It is what? The angle between any two adjacent bond is known as what? Bond angle. It is represented by degree, minute and second, right? And what are the factors which will affect the bond angle? It is what? Hybridization of the central atom. Okay. Next is presence of lone pair. It will also affect the bond in, it will also affect the bond angle. As you can see, hybridization of the central atom, percentage of S character increases. If the percentage of S character is increases, bond angle also increases. Okay. Now if we are talking about the lone pair, so lone pair, the bond angle is inversely proportional to lone pair. Means what? If lone pair will increase, the bond length will decrease, right? Now next is electronegativity of the central atom. If the due to the more electronegativity of the central atom, the bond pair gets shifted towards it, and the distance between them decreases. Thus further bond pair repulsion increases. So what we can say, bond angle is directly proportional to electronegativity of the central atom, right? Because due to this electronegativity of the central atom, bond pair get shifted towards it, and the distance between them decreases. Thus we can say bond pair repulsion increases. So bond angle is directly proportional to electronegativity of the central atom, right? Now again, last one is multiple bond. So when we talk about the multiple bond, electron density of the for a double bond is more than in a single bond. So the repulsion in double bond is more than the single bond. So what we can say, that the bond angle is directly proportional to number of bond. Okay, or we can say number of double bond, right? So I hope you have understood this bond length and bond energy, right? Next is formal charge. We have already discussed in the previously formal charge, right? So I hope you have all know how to find out the formal charge. What was the formula of formal charge? Number of valence electron for an element minus number of bond of that atom minus number of unshared electron, right? So how to calculate, you can see here we have done this also in the first lecture. We have discussed about this, right? So this was all about the chemical bonding and molecular structure. I hope you have understood this chapter. So in case of any doubt, you can let me know in the comment section. Okay, so from the next class we will start a next chapter. Till that, thank you.